Hi, in today's video I would like to introduce a very nice problem of New Zealand Mathematical Olympiad. Sorry, but I'm not sure which year this problem. Okay, so anyway, find all positive integers and such that we have this statement or condition: n factorial plus number 3 is a perfect square. In the other word, we are going to find all integer n based on this condition. So this condition n factorial plus 3 must be a perfect square. Okay, so the hint that I'm trying to give to this one, how to deal with the terms of n factorial. Okay, how to make kind of factorization to make this term on the form of perfect square. Okay, just first thing, you try to abuse cases to try the how goes, and for example 3 factorial, 4 factorial, and so on and so forth, to see what's the form is taking. Okay, so let's jump into the solution. Let's check 4 factorial. Okay, for 4 factorial is giving us 4 is multiplied by 3 is multiplied by 2 is multiplied by 1. I'm going to transfer this one on the form of the square. Okay, let's take number 4 is 2 to the 2 is multiplied by y1, for example. Okay, I don't care about other terms. I'm taking just 4 and make it as a perfect square. Okay, so let's check with the 6 factorial. 6 factorial is 6 is multiplied by 5 is multiplied by 4 is multiplied by 3 is multiplied by 2, and so on and so forth. Okay, I have 2 here, I have 4 here. 2 is multiplied by 4, which is 8. 8 is multiplied by 2, 16. 16, this one I can rewrite it as 2 is multiplied by 2 quinary square is multiplied by y2, for example. Right, so for this one, 2 is multiplied by 1 quinary square. Let's move on to 8 factorial. 8 factorial is the same thing as 8 is multiplied by 7 is multiplied by 6 is multiplied by 5, 4, 3, 2, 1. Okay, I will have the same thing here. I will get 2 is multiplied by 3 quinary square is multiplied by y3. 2 is multiplied by 3, 6 quinary square is 36. So 36, I have 6 here is multiplied by 2 is multiplied by 3, 6 is multiplied by 6 is giving us 36. It's not necessary to pull out all the terms. I'm pulling out the terms which I need. Okay, so if you take a look carefully here, I have a kind of patterns here. 2 is multiplied by 1, 2 is multiplied by 2, and 2 is multiplied by 3. Okay, so I'm going to apply the same rule on n factorial, but n is superior or equal to 4. I'm going to start my factorial from number 4. So I will get n factorial equal to n is multiplied by n minus 1 and all the way down. So I will have same form as 2 is multiplied by k minus 1 quinary square. Okay, is multiplied by y3. Okay, so I'm going to pull out number 2 outside. Is giving us 4. Okay, 2 to the 2, 4 is multiplied. This one will be multiplied by y3. I will get y hat. This one is congruent to 0 mod 4 because 4 is a multiple of 2. 4 divide 4. Okay, so now let's move on to our question. We have n factorial plus 3. Here is a problem. We are going to prove this n factorial plus 3 is not a perfect square when we have n is superior or equal to 4. Okay, so this one not a perfect square. Okay, I'm going to use the absurd proof. We assume is a perfect square. At the end of the term we will find a contradiction. Okay, we assume n factorial plus 3 equal to p square as a perfect square. Okay, so equivalent, this one equivalent n factorial plus 3 equal to m p square. It exists m is an integer, but m, we take a particular case when m equal to 1. In order to have this one a perfect square, you have to have m equal to 1 as an integer, okay? So this is divisibility definition, because this one equal to this one, that's mean p square is divide this one, okay, to have an integer m. But to have a perfect square, you must have m equal to 1. So assume this one is correct. We have n factorial plus 3 equal to m p square. Another thing I try to mention here, this n factorial is written on this pattern, okay? 2 is multiplied by 1, 2 is multiplied by 2, 2 is multiplied by 3, okay? We have number 2 all over, okay? So also I'm going to transfer this one in the same form. So I'll get m is multiplied by 2 times k prime. It's not necessary to have the same key that I have here. K prime quinary square. I'm going to pull out number 2. I will get 4 is multiplied by m k prime square. I'm going to call this one as a 4 x hat, okay? Then I'm going to bring this n factorial to this side. I will get number 3 equal to 4 x hat minus n factorial equal to 4 x hat. I'm going to replace n factorial with 4y hat minus 4y hat. By taking 4 as a common factor, I will get 4 is multiplied by x hat minus y hat, which is congruent to 0 mod 4, because both of them are mod of 4. 4 is divide 4, okay? This one is telling us 4 is dividing 3, which is ridiculous, okay? Okay? Which is contradiction. That's mean we don't have a perfect square when we have n is superior equal to 4, okay? Always you put n is superior equal to 4 here. Let's move on to find the solutions of this equation when we have n is strictly inferior than 4, okay? Now we have n factorial plus 3 equal to p square as a perfect square. We found for n is strictly inferior than 4 because we found no solutions when we have n superior equal to 4 due to the contradiction that we found in the last board, okay? So I'm going to check n equal to 1 as an integer, as a positive integer. N equal to 1 is given as 1 factorial plus 3, which is equal to 4, which is 2 quinary square equal to p square. So we found n equal to 1. This is the first solution, okay? Let's check. We have n equal to 2. We have 2 factorial plus 3. 2 factorial is 2 plus 2, which is 5, equal to p square, which is not perfect square. Let's check with n equal to 3. Simplifies 3 factorial plus 3. 3 factorial is 6. 3 is multiplied by 2 plus 3. 6 plus 3 is 9. 9 equal to 3 quinary square, which is p square. That's mean n equal to 3 is a solution as well. So the only solution that we have n equal to 1 and n equal to 3. Okay? Now I have ended with this proof. If you are interested in watching this one, don't forget to support us with your like and subscribe. Thank you for watching. I will see you in next video. Bye.